Our third speaker of today is Guido Jouret. Guido is the Chief Digital Officer from ABB. Please join me in welcoming Guido.
Thank you, Michelle. Thank you very much. So you've heard two very different presentations already today. Allow me to introduce a third. And I feel a little bit like I'm carrying coals to Newcastle, as they say in the UK. I'm telling you why AI will drive the industrial world, the Internet of Things, to the cloud. Of course, this is a whole cloud conference, so it seems like we're stating the obvious. But let me bring you a little bit into my world. I work for a company called ABB, and it's not Airbnb, it's a Swiss industrial company where we make robots, we make electrical gear, transformers, motors, and we've been around for 130 years. And we are witnessing some of the biggest changes happening to our world that we've ever seen. And some of you have probably heard about the fourth industrial revolution. Let me back it up a little bit and explain how we got here. So in the beginning, we used muscle, we used brawn, and in 1784, the steam engine was invented, and it allowed us to dramatically increase the amount of power we could deploy by using steam. That was the first industrial revolution. That unleashed a whole bevy of productivity in terms of factories, mass-producing goods and materials. And then in 1870, and our company was quite instrumental in this, we introduced electricity. And a steam engine was really powerful, but it was also very big. Electric motors are small, and you can deploy them more widely in many more places. That was the second industrial revolution. And some people think that the fourth industrial revolution is all about the advent of computing. But actually, we've had computing in the industrial world in terms of programmable logic controllers, embedded systems, SCADA environments, industrial PCs, for quite a while, actually going back to the late 1960s. So what's different with the third industrial revolution, which was really the advent of automation, digital technology, controlling the electrical systems, controlling the mechanical environments, and this fourth industrial revolution? And I think primarily it's because we're moving from systems that can act and react to systems that can plan and learn. The introduction of software-defined capabilities driven by the cloud. And the transformation that this is engendering cannot be overestimated. It's changing the way we produce goods in factories, it's changing the way we do transportation, and it's also changing the way we produce energy. And this progress over about 250 years has dramatically changed how all of us live. But it has come at an incredible cost. The benefit is that if you go back to when the steam engine was invented, average life expectancy was 37 years old. Today, we enjoy life expectancies in most of the world that's double that, if not more. But we have a problem. And I call this problem iOS. And no, it's not version 13.2, although I have some problems with that too, but it's about the industrial operating system. It's the way in which we provide energy, food, water, transportation. Because in the industrial way, we achieved tremendous gains in productivity through centralization and making things very, very large. Large power plants, highly centralized, big farms, big manufacturing plants, gigafactories, but the future will not look like this. In fact, in the future, most of us will be living in cities. 75% of the world's population by 2050. And the reason why iOS 1.0 will not work anymore is because the way we're running the world is killing our planet. And so we need to find smarter ways of providing buildings, because 40% of the energy we produce goes to buildings. We need to find better ways of transporting goods and people, because 25% of our energy goes to transportation. We need to find a cleaner and greener source of energy because the fossil fuels that we use today are causing hundreds of billions of dollars of damage to people's health. And we also need to find ways to treat and distribute water in more effective ways. In California, where I live, 20% of all of the energy that we produce goes to moving water. We live in a dry state. But that will be the future in many more parts of the world as well. So we need an iOS 2.0, a new system based on small-scale generation, assets that are digitally connected, digitally controlled, and increasingly intelligent. And so I'm going to use the example of electrification because, as you saw in the previous slide, almost everything we talk about, whether it's transportation, whether it's water, whether it's food, is all driven by energy. And in the future, most of that energy will take the form of electricity. And let's consider transportation. If we electrify all forms of transportation, we'll need 75% more electricity by 2050. We'll start with things like buses and trains, already mostly electric, at least for new buses and trains. We'll also do passenger cars. Today in California, about 5.5% of new passenger cars are electric. So that's good, but we still have a ways to go. That funny thing you see on the water is something called a sea bubble taxi. It's in Geneva, Switzerland. It's electric. And we'll also eventually get to trucks and planes. A bit more difficult to do because the battery densities don't currently support long-range travel very well, but there's a lot of progress being made. So imagine that we're going to shift away from burning fossil fuels for transportation, and we're going to load that up onto the electricity grid. What would that look like? Well, it looks a bit like this. Because while we're adding more loads onto the grid, the source of that power on the grid is shifting as well. So today in the United States, about 17% of our energy comes from renewable sources. California is a bit higher. It's about 30% and going up. And this chart that you see on your left-hand side is known as the California Peking duck. You won't find it in any restaurant. What it starts to show is the shift of the net demand of electricity during the working day. And as recently as 8 or 9 years ago, peak energy demand was in the middle of the day. It was hot, air conditioners kick in, and that's when you had the most demand for power. As a result of the investment in solar panels, however, in California, that natural sort of peak in the middle of the day is turning into a trough. If we now add electric cars that are going to come onto this grid, which will mostly start to get plugged in at night when people return home, we're going to start seeing a huge shift of energy demand into the night, early hours of the evening. And this volatility in the supply of energy and the demand of energy is volatility squared, because we're putting more loads onto the grid, and the source of that power, solar, wind, is also inherently volatile. So how do we manage that in iOS 2.0? Well, the enemy is volatility. And as consumers, if you leave the lights on or you consume a lot of electricity today, you'll pay a premium for that extra spike in consumption. What you may not realize, though, is that if you're a commercial customer, meaning if you're this hotel, or you're a factory or a plant, demand charges, that spike that you see on this graph, will determine the rate that you pay for the entire month, and in some countries, for the entire year. So there's an extremely strong incentive sent via a pricing signal to a commercial user of electricity to shave those peaks. But how do you do that? Well, in the future, the energy grid will no longer be the thing that sits behind the meter. It'll be inside of your buildings. And this grid, or a microgrid, is going to have loads, meaning the lighting systems, the elevators, all of the things that consume electricity. It would also have sources of generation. It might have solar panels on the roof. It might even have a small wind turbine. And increasingly, there will be energy storage in terms of batteries. A lot of those batteries will be second life batteries coming from electric cars that still can serve a purpose once they're no longer as efficient inside of your vehicle. And all of these systems, in order to work, to shave these peaks, to know when to store energy, when to yield energy back, when to sell energy onto the grid, when to buy it from the grid, all of those systems inside of buildings have to become intelligent. And instead of one massive renewable grid, we will have millions of microgrids, all communicating, all coordinating. The challenge, of course, is the expertise. And I drew this graph after a conversation with one of our customers who pointed out that the moment of peak know-how that customer had was the day that we shipped them some new smart machine. That was like 100% know-how. We've been trained, we read the manual, we know how to use this. Great. And then it's downhill from there. Why? People leave, they retire, you forget, and so there's a natural erosion of skill and know-how. And in a world where a lot of the infrastructure will increasingly be built up of smart machines, we need to find ways of supplementing that erosion of knowledge, especially because a lot of this infrastructure lasts for decades. The people who buy it will leave it to their successors and sometimes to their successors. So the only way we can bridge that knowledge gap in smart infrastructure is to invest in standardization, open standards, making things more modular so that they're easier to put together, you don't have to figure out as much. And two that I'm going to be focusing on for the remainder of this talk, teleoperation and autonomy. So let's think about autonomy for a moment. What is autonomy? We tend to think of autonomy or autonomous cars, which is maybe the example that most of you immediately go to, as kind of like a binary condition. It's like it's not autonomous and it's autonomous. But it's really not. In fact, it's a continuing evolution towards increasing levels of autonomous operation. And at the base level, the humans are in charge. The human's still in charge, but there's some assistance. Think like cruise control in your car. Think about maybe a rudimentary automation system inside of a factory. In the third level, the machine leads and the human supports. In the fourth, the machine leads and the human sort of checks in from time to time. We call this transition from human in the loop to human on the loop. And of course, at level 5, there may almost never be a reason to phone home and to ask for help. And we believe this level of autonomy will pervade all of this smart infrastructure in iOS 2.0. So it's not only the buildings, it'll be the factories, it'll be the grid, it'll be ships, it'll be buses, it'll be trains. All of that infrastructure is increasingly going to be intelligent. And let me give you an example, because so far I haven't actually backed up with proof points what I say. This is an example of a circuit breaker that we make, and this is part of what we call our ABB Ability portfolio. These are smart and connected pieces of infrastructure. And this circuit breaker is like your smartphone. It runs apps. So while it's sitting there in the basement protecting the circuits, it can do more. What can it do? It can measure the quality of power coming into the building. It can measure the loads on that building coming from all the different floors or the different parts of the factory of that building. It can also manage the energy generation, the energy storage, the heating system, the cooling system. So some basic building management know-how can also be provided as an app. And then we can extend this with third-party applications, such as predicting the weather, and in one in particular, which we recently announced, leveraging AI to predict these future peaks in power consumption, so you can hopefully shave those peaks and avoid those demand charges. So now let me talk why this is going to trigger an investment in AI, and specifically towards the cloud. And for the last 15 years or so, I've been in various roles where I've been saying computing is moving to the edge, It's all about the fog, edge computing, and I worked on a number of products that enable that. Well, I think the answer is a bit more nuanced. I think it's not just edge or just cloud, but there's definitely going to be a huge focus on the cloud in the industrial world, which up until this point hasn't really embraced the cloud. And it's going to go like this. The AI applications we need to make this infrastructure smarter, how do they get trained? How do we train a ship to navigate increasingly by itself? How do we teach a building to operate within safe conditions? How do we train a forklift to be able to move around inside of a factory without hurting people? We need to create not only the AI, but we need to infuse it with domain expertise. We have to tell it about the world. We have to tell it about the laws of physics. And then we need a digital twin, because in order to make this AI learn, we have two choices. We can take an autonomous vessel and then have it sort of randomly crash into sailboats and harbors and things like this until it stops doing that. Or we can create a virtual world in which it can happily learn quickly, and then once it's proven itself there, we can then unleash it into the real world. And therefore, I think we're going to see sort of a natural evolution. We're going to start with, let's first connect these intelligent infrastructure pieces. Then we'll have some kind of system to monitor it and make sure that it's not about to fail. Better yet is when we can predict that it's going to fail, and this is where the injection or the infusion of AI will start. And then we're going to find a way to overall increase the performance of these assets. One thing that many of you may not realize is that a lot of this iOS 1.0 infrastructure is dramatically inefficient. Half of the food we grow is thrown away or rots before it is consumed. We have manufacturing plants, among the best of them, that are only at 45% of their total theoretical output. The electricity grids typically operate at about 40% capacity. So if we get serious about optimizing the performance of this industrial infrastructure, we can do much, much better. And lastly, we can unleash all kinds of new and innovative models where we could potentially sell these infrastructure in new and innovative ways. So how do we get to the cloud? The promise of AI is that it's going to allow us to have all this smart infrastructure largely manage itself. But today, that is not the reality of how the industrial world works. The reality is today that almost everything you can think of from a digital perspective is on premises. It's in the factory, and it's not in the cloud. And when you look at it, what you discover is there's two kinds of applications. One we call the control loop. And the control loop, typically today, this is using devices such as programmable logic controllers, SCADA systems, distributed control systems. These are sort of like the digital nervous system of a factory or a plant or a refinery today. And they sense, they analyze, and they act. And those are mission-critical loops. If something goes wrong, the factory breaks down, the chemical plant blows up, people get hurt. But there's another loop. And this is the asset loop, where you sense, you analyze, and you act, but you're not controlling the microsecond level response time of something. You're maybe just boosting the energy efficiency of this asset. You're increasing the yield by synchronizing the inputs and the outputs a bit better. So the cycle times tend to be minutes, hours, days, or weeks. So we'll start with all on-premises. This is the world of today. This is what industrial IT systems look like. The next step is when we recognize that we can make these systems smarter by adding AI to do this predictive maintenance, to do that condition monitoring. But where do we train the AI? And we have an example of this. We've recently created an application where we can sort through some trash. We can recognize different types of trash with a robot arm and then pick it up and move it into the right bin. To train this AI, you need oodles of compute. You need large data sets. Where do you do that best? In the cloud. But what you may not want to do is to close that loop between analysis and action and cause that action to be triggered from the cloud. Today, I would say most of the customers we have, they say, look, cloud for analytics, yes. Cloud for control, I'm not quite there yet. But I believe that that's simply the next logical step, to close that loop, to let an AI system in the cloud actually make a decision and send the instructions to cause something to happen. So now you close that asset loop. But we actually have customers that are starting to go all in, and they're saying, no, no, no. In the future, the sensing and the acting, that's sort of like my eyes and ears and my arms and legs, but I'm going to put my brain in the cloud. Why? Because I can get faster innovation, better integration. All of the benefits we have on the IT side for the cloud also apply for the OT, or operational technology side. And therefore, I think it's inevitable as customers look to manage more of their systems through increasing levels of autonomy, they're going to naturally embrace AI, and on that journey to AI, it will naturally lead them to the cloud. So what do these eyes and ears and arms and legs look like? Well, they don't look like Arnold Schwarzenegger, but they might look like this. One example is our data center sheriff. This is a robot that goes into very large data centers and can swap out servers and disk drives and power supplies and things like this. And that can be scheduled. It can be given a set of tasks to do. And why not? Those data centers are getting very, very large. But we also have something more mundane called a motor crawler. So the casing of an electric motor, it looks like a metal drum. Inside are the coils and the windings, and between that casing and the windings is a bit of space. So we've made a robot that's kind of flat like a pancake, which you can insert in this inner space, and it can then go around and visually inspect the inside of the motor to make sure that it's still good to go for another couple of decades. And then in our transformers, so these electrical transformers, most of you recognize transformers as these drum-like things that are on a pole in the United States. Well, big transformers are more like these rectangular cubes. And the coils and the windings are in a bath of mineral oil. And if you want to do an inspection, you have to basically empty out all this oil, look at the windings, and then put it all back. The transformer diver is essentially a small, completely sealed robot that we can plunk inside of this mineral oil, and it floats around and it navigates inside, sending back images over Wi-Fi. And then the plant helicopter is a drone equipped with various sensors to detect methane emissions and other noxious gases, which can also help tremendously in terms of automating and controlling things. So these are the kinds of ways in which an AI or a brain in the cloud will sense, analyze, and act on the real physical world tomorrow. And increasingly, these will be more and more autonomous. In the beginning, they're probably level 1 autonomy with a human being doing most of the control and validation. But the next step beyond that will be that these systems become more and more self-sufficient. And while most of you know about Moore's law for semiconductors or Metcalfe's law for networking, I'd like to suggest that we need a law for AI. And the way to gauge the intelligence of an AI system will be to measure how many people we have versus these semi-autonomous systems. So today, for example, the kind of robots that move around inside of supermarkets taking inventory, the rough rule is 10 to 1. You got 10 of those, you need 1 operator, just to make sure that it doesn't get stuck or backs into a cardboard box and can't move anymore. But as these systems get smarter, we'll go to 100 to 1. We'll go to 1,000 to 1, because more and more these systems will be able to handle a lot of these corner cases, be able to make decisions, and not only to act and react, but to plan and learn. So I believe that increasingly we're going to measure the system's intelligence based on what I call an autonomy quotient, the ratio of people to semi-autonomous things. So if that's the case, do we still need people? And we believe that actually, as good as AI is, and we do need it, because all of this iOS 2.0 is going to rely on lots and lots of smart infrastructure that for most of its life, for most of what it does, will manage itself. But as we also see almost every day, AI today is limited. It's brittle. If the thing you wanted to show it wasn't covered in the training set, you don't quite know how it will behave. And If you're analyzing something like cat videos, it's not a big deal. But if you're running critical infrastructure where people's lives and their health depend on it, it is a big deal. And that's why we think that we're going to see for quite some time to come a combination. People are really good at being flexible, being creative, adapting to unknown circumstances. The AI is very good at applying a rigorous formula to data that it's been trained on, and it never tires, it doesn't have to sleep. And therefore, the best combination is when you put the two together. We call that a humane. And this humane has been proven to outperform AI alone or humans alone. In the cases of, for example, analyzing X-rays and looking for cancers, or recognizing images in criminology cases, for example. So we think that in control systems or operating complex machinery, the best combination will be essentially a symbiosis between AI and people. Thank you very much.